All right, I think we can start. Welcome everybody to this webinar series about beyond diagonal reconfigurable intelligent surfaces. This series is organized by the Special Interest Group on BD-RIS within the IEEE Communication Society. And my name is Matteo Nerini. I am one of the officers of the Special Interest Group, and I will be your host for today. Today we are starting the second season of the webinar series, building on the success of the first season that happened last year. And today is the first webinar out of 8. There will be a webinar every other Wednesday from now until December. And today is my great pleasure to introduce you Professor André de Almeida from the Federal University of Ceará. So let me briefly introduce our speaker. André is a professor in the Department of Teleinformatics Engineering at the Federal University of Ceará in Brazil. He has been awarded multiple visiting professor positions at the University of Nice Sophia Antipolis in France. His research interests include signal processing for wireless communications, tensor array, and multi-channel processing, multilinear algebra, and wireless communication. A significant portion of his research has focused on tensor decompositions with applications to wireless communications. He has published over hundreds of papers, 6 book chapters, and 7 patents. Professor Almeida is currently senior area editor of the IEEE Transactions on Signal Processing and IEEE Signal Processing Letters. He is an elected member of the IEEE Signal Processing Society Signal Processing Theory and Methods Technical Committee and of the EuroSIP Signal Processing for Multi-Sensor Systems Technical Area Committee. He currently serves as the chair of the SPMUS PAC. Prof. Almeida has also served as an associate editor for several journals, including IEEE TSP, IEEE Signal Processing Letters, and IEEE TVT. He served as the IEEE SPS Director at Large for Regions 7 and 9. He was appointed Chief Editor of the IEEE SPS SIG and has been involved in organizing and chairing several IEEE Signal Processing Society conferences. He's a co-recipient of the 2018 IEEE Communication Premium Best Paper Award and of the 2022 IEEE Signal Processing Premium Best Paper Award. He also received the Best Paper Award at the 19th International Conference on OFDM and Frequency Domain Techniques in 2016, and the WCNPS 2022 Best Paper Award. And finally, he was elected in 2018 a member of the Brazilian Academy of Sciences. So before starting the webinar, let me remind you the rules. The talk will last approximately 50 minutes, during which we will be muted. And if you have any questions, feel free to type them in the chat. After the talk, there will be a 10 minutes Q&A session where 2 to 5 people can be unmuted and can ask the questions, or I will select questions from the chat. So enjoy the webinar, and André, the floor is yours.
Okay. Do you see my screen?
Yes.
Great. So hi, everyone. And thank you, Matteo and Bruno, for organizing this webinar series and for inviting me to give a talk. Yeah, today we are, I will show you some recent results on the topic of channel estimation for beyond diagonal reconfigurable intelligent surfaces using from a tensor decomposition perspective. This is a joint work with my colleagues Bruno Socal, Hongyu Li, and Bruno Clerc. And this is the landscape of our city, Fortaleza, on the northeast of Brazil. So just to for you to have a small sample of the nice view of the seaside. Well, so first of all, let's talk a little bit about the motivation for this problem. So as many of you are aware of, beyond diagonal reconfigurable surfaces, they have been a topic of subject to quite intensive research over the past couple of years. And I will not talk deeply about that. There will be other talks also focused on the surface architectures and on optimization algorithms in this webinar series. So I will just briefly show you the high-level view of a BD-RIS. So here you have a communication link between a base station or a transmitter and a receiver via beyond diagonal RIS. And in contrast to the sort of most classical diagonal RIS architectures where the scattering elements or the impedances are not interconnected, in the beyond diagonal RIS, we introduce or we have cross connections between the elements which are modeled via impedances, and this adds an additional degrees of freedom to control the electromagnetic wave impinging on the surface, and of course that translates into, as has been shown in previous work, translate into capacity gains or coverage, or even more, degrees of freedom to handle interference. Let me just put my laser here. I'm not sure if you see it. Yeah. Okay. It's moving in. Yeah. So, yeah. Despite this advantages of BD-RIS, there are some bottlenecks, and I will tackle one of them in this talk. I mean, the first one is implementation complexity. Of course, this comes from the fact that you have more elements interconnected, and there are a number of hardware aspects that come along with this. So there is no free lunch, of course. But the other bottleneck related to BD-RIS concerns channel training and channel estimation. And this is the topic I'm going to address here. And if we suppose a BD-RIS with n scattering elements, for instance, we can, of course, have an architecture where you partition the surface into Q groups, and every group has size n bar, when then n is the product, is the total number of elements given by the product of n bar and q. So, and here, if you assume lossless or symmetry constraints, this scattering matrix associated with a certain group, they satisfy those constraints. So, what is the main bottleneck regarding channel estimation? Yeah, first of all, if you compare with diagonal RIS, where these interconnections do not exist, here, adding those additional degrees of freedom complicates a little bit the channel estimation process. First of all, because you should cope with those constraints. And then at the end, since we increase the number of connections, in principle, the number of pilots that you need to estimate those channel matrices H and G, right? It's significantly higher, the overhead, if we compare with single connected or what is so-called diagonal RIS, right? This paper, a couple of years ago, addressed a channel estimation problem for BD-RIS based on a least squares solution. There are some problems related to this technique, although the optimal design was derived in this paper. Usually, what we observe is that when the group size and bar increases, the performance degrades. Also, there is a high training overhead related to the number of the length of the training sequences that is required to optimally estimate these channel matrices here. And then what I would like to point out and to emphasize is that the low rank structure of what we call composite channel is not exploited here. So in this method, the overall cascaded channel is estimated as a whole, and you see the whole link as a black box. Although this makes the problem simple, tractable, and simple, these solutions do not really see the chronicle structure that is embedded into this composite channel, which I will show you in a few minutes. Here we have the structure of the talk. And coming back to the point I was here, the signal model at the receiver after matched filtering with the pilots. So we assume that pilots are orthogonal, and then we eliminate them by matched filtering at the receiver. And then we are left with this signal model here, right? So Y of K represents this the post-filtered signal at the block K. And then we have here a summation of Q components. And then you see here the cascaded channel in the BD-RIS matrix S of K, right? And the B of K is the resulting noise. Well, so just a little bit of notation, if I can, so that we are on the same page. So here we have a matrix. We will make use of the VEC operator, which vectorizes this matrix and stacks those columns one below the other. And then we have the unvec, which basically does the opposite. A diagonal operator constructs a diagonal matrix with one vector. This product will be very important here in the talk, which I suppose you all know. So the Kronecker product, but anyway, this is if you have two matrices W and Q, then the Kronecker product basically spreading generates a larger matrix by taking every single element of the first one and then multiply by the whole second matrix, and then that spreads the dimensions. We have on the other extreme, which would be also useful here, the Cauchy-Rao product, which is a column-wise Kronecker product. So if you have two matrices that have the same number of columns, R, then their Cauchy-Rao product is indeed the concatenation of column-wise Kronecker products of the corresponding column of H with the corresponding column of G. And in between both products, we have what we call the block Kronecker product, which indeed, if you partition the matrix H and the matrix G, in our case, it would be the channels, right? If you partition those matrices into Q groups, then the block Kronecker product is indeed the concatenation of Kronecker products, and those Kronecker products, they are confined within blocks, right? So what you have here is a concatenation of Kronecker products block by block. Okay, so coming back to the least squares channel estimation scheme I was talking earlier, if we vectorize that Y of K matrix that I presented previously, by vectorizing this element here, I remove the noise term for simplicity, okay? So we just work with the useful signal part. And then if we vectorize this useful signal part, what we end up with this Kronecker product involving the H of Q and the G of Q. And of course, we have on the right-hand side the VEC of the scattering matrix of the block Q. And then you translate that summation into a matrix-wise representation, right? And then what we end up at the end with this notation here, where we have the received signal vector at the block training block K, which is given by now the block Kronecker product between the channel matrices H and G, and times the VEC of the scattering matrix that you obtain, the scattering matrix that concatenates indeed for all the groups, and then you have a long vector S bar, which is the vectorized form of this whole vector here, right? And finally, of course, we want to exploit the whole measurement, so we collect the received signal during the K blocks in a matrix Y. Remember that, I mean, this matrix is indeed, it contains the dimensions of your received pilot signal. So MR, number of antennas at the receiver, times MT, number of antennas at the transmitter, and then as columns, you have K columns. So this contains the whole measurements that you collect. And we can, of course, arrive at this simple equivalent linear model where we have Y equal to T times S bar transpose plus noise. And but in particular, the T matrix is indeed given by the block Kronecker product between H and G. And our goal is to estimate H and G from the measurements, right? The first way to do that, which was shown in the previous work by Bruno Clerc and his co-authors, is that, okay, once you have this problem here, and then this is basically a traditional MIMO channel estimation problem where the goal is to design the best BD-RIS scattering matrix S bar such that you achieve the best performance of this linear estimator with respect to the estimation of T, okay? Let's do some comments about this. So this here, we have a traditional MIMO channel estimation problem with constraints that are imposed by the BD-RIS scattering matrix and the symmetry and lossless constraints, which leads to orthogonality of this S. So in that paper, I mentioned the authors, they proposed ways of designing this matrix S. That was quite nice. However, we have as a bottleneck of this solution is the high training overhead. This is one first point. And this sometimes comes from the fact that we treat the composite channel T, which is this T, remember that T is the block Kronecker product between these two channels. The T is interpreted as a MIMO channel, right? And then the structure that is embedded into this T is not exploited. This results in a requirement that can be limiting depending on the scenario. So which requires indeed that the number of measurements of blocks you need to collect at the receiver must be at least equal to this amount here, which is n bar squared times Q. So n bar is the group size, right? And then Q is the number of groups. So if you scale the BD-RIS as you have larger groups or stronger interconnection between those impedances, this increases the K to the square of the size of the group. Okay, and this is one point. And then the other point, as I mentioned, is that the Kronecker structure of this equivalent MIMO channel T, it's not exploited in that traditional least squares method. And then with that in mind, I will show you two solutions that indeed overcome both problems, or at least one of them. So the first one is the BTKF, the Bloch-Tucker-Kronecker factorization algorithm, which is a closed form method to find the constituent channels H and G once you get the T, and then you can apply an additional refinement step to decouple the equivalent channels H and G from this MIMO channel, the equivalent MIMO channel. And then there is another solution based on tensor decomposition, which is the BTALS. And this one is an iterative method that the main advantage of this one is that we can significantly reduce this K, which indeed is the training overhead. So that can overcome this training bottleneck I mentioned earlier. Okay, so again, we have, so why decouple is important? Indeed, our goal is to indeed, instead of estimating this black box MIMO channel, we want to go deeper and then to open up this box and then find the constituent channels H and G. This is very important, for instance, if you want to separately sense the links between the BD-RIS and the transmitter, which might be, let's say, changing at a different speed or pace as the link between the BD-RIS or the receiver. This is, for instance, one motivation for decoupling the channel. So if, let's say that the channel G changes at more faster than the H. So when it comes to re-estimate the cascaded channel, we can keep one fixed and then estimate only the second one. So this allows to reduce the training overhead. And also when it comes to optimize beamformers and combiners and precoders, etc., this is usually done based on the individual channels H and G. So anyway, it's useful to decouple these two channel matrices from this T matrix, right? So here I just give you a overview of the block diagram. So the least square scheme, you start with the measurement matrix Y, and then with the knowledge of the BD-RIS training matrix, and then you apply least squares, you get the T, and then you stop. The second class of channel estimation methods, which I call channel decoupling schemes, is indeed the first step here of the first solution is the least squares, and then you add a decoupling stage after that where you find G and H. And then the second decoupling channel decoupling scheme is the BTLS. Indeed, you start with a tensor, which I will show you later, this tensor. So this tensor contains the measurements, is a rearrangement of this matrix in a 3D array. And then you possibly use the knowledge or not of the scattering tensor. And then this provides you direct estimates of G and H without having to pass by this prior least squares step, right? So these are the two algorithms I presented in these two papers. Okay, so a little bit of tensor decompositions. Anyway, well, we are going to need some useful concepts here. So in a nutshell, so a tensor is a multidimensional generalization of a matrix or a higher order array or even a multidimensional array with three or more dimensions or modes. So here I show you a tensor of order 3 or a three-dimensional array with dimensions ijk, okay? And one particular aspect of the tensors is that in the matrix case, you can transpose the matrix or work with the transpose or not. In a tensor, the way of transposing it is a little bit different. So this is linked to the concept of unfolding. So in order to arrive at that, if you note here, this cube, it can be sliced in three different ways. We can indeed slice this cube in terms of its frontal slices, y.k or x.k, and every slice is of dimension I times j, or you can slice this cube in the horizontal direction, then we collect another set of matrices x, I, y, I dot of dimensions k times j, or the third way to slice this cube is taking vertical slices, and then you get indeed a collection of matrices of dimensions k times I, right? And then from these slices, from each set of slices, if you stack them next to the other, you will obtain what we call in the tensor literature the unfoldings or the matricizations of this tensor. And this can be seen, this x of 1, of 2, and 3, can be seen as three different ways to arrange the same data, because the same data stored in this tensor is contained in all these three matrices, but they are arranged in different forms, okay? there are two main decompositions that we usually see in the literature. The first one is the power-factor decomposition, or the power-factor decomposition, which indeed decomposes a certain tensor in terms of three-factor matrices, A, B, C. And indeed, this can be seen as a latent variable representation of this tensor. So what is the idea of parafac? This is a low rank decomposition. So you have, let's say, a large tensor, I times j times k, and then you, by finding the best decomposition of this tensor y, you get these three-factor matrices that indeed represent the essential information contained in the tensor y. And this first equation is the representation of the tensor in terms of the outer product of three vectors, and this is the outer product of operator. And then you have R as the rank of this tensor, right? So if the dimensions of the tensor are very large and the rank is low, this decomposition indeed provides a way to have a compact and low rank representation of a high dimensional data. This has been used in different areas, not only in wireless communications, but also in data mining, machine learning, and filtering in other or imaging. A number of applications have resorted to this low rank decomposition as a means to compress the information, right? And then in the parafact decomposition, of course, the goal is, once you have the tensor y, find the best ABC that minimizes, let's say, the least squares fit or any other loss function with respect to the measurement tensor y. As I mentioned in the previous slide, we can unfold the tensor into three different ways, and it can be shown that every unfolding admits a different factorization or representation in terms of the Cati-Rao product, which is this column-wise chronicle product I talked earlier. And if you see here, this is a kind of cyclic permutation, right? So the first mode unfolding can be represented by like A times C Cati-Rao B transpose, and then the second and the third one, they are basically cyclically shifted versions of these representations by changing the positions of the matrices, all right? And these unfoldings, they are quite useful when it comes to optimizing and then finding the best ABC from the measurement data. The second decomposition, which we indeed use in this work, is the Tucker-3 decomposition. So the Tucker-3 is a sort of generalization of the parafact decomposition, and where we again have the three-factor matrices ABC, but now they do not necessarily have the same number of columns. And we have here a core tensor in the middle, which indeed can be seen as a weighting factor that weights the corresponding columns of ABC to generate the final tensor Q. So if you compare with the parafac, as I show here, this core tensor is indeed an identity tensor that has ones in this main diagonal and then zeros elsewhere, where in the Tucker decomposition, this tensor in principle can take any form, and can be a dense or a block sparse or a structured tensor. And then again, following the same reasoning, we can represent this tensor as in terms of the outer products of the corresponding vectors of ABC. The matrices now, they have different number of columns. And then again, we can come up with a similar way of representing the unfoldings of this tensor y in terms of the factor matrices. And now the difference is that we have the core tensor in between, which is the unfoldings of this G tensor here, right? And then as a particular case of the Tucker decomposition, we have the block Tucker or decomposition, which is basically the same as I presented before, but now in terms of partitioned matrices AB. And we don't have the matrix C, we have a Tucker 2. The 2 here means that we only have two matrices, and then the third one is equal to the identity. And in particular, the word block means that this tensor is block diagonal. So it is a concatenation a diagonal, let's say, concatenations of different tensors in this way. And of course, every tensor is associated with a given matrix A and B of this whole block matrix here, right? So there is a one-to-one correspondence when it comes to generate the output between each color is coupled to the same here. So A1 with G1 and B1 plus A2 times D2 and B2 plus etc. until AQ, GQ, and BQ. As we are going to see very soon, the received signal after matched filtering at the beyond diagonal with BD-RIS assisted communication follows exactly this model plus noise. And indeed, this is what we exploit to estimate the channel matrices H and G, which now are shown here as in terms of A and B. So translating that, making the link between the general Tucker decomposition and our measurement model for BD-RIS training, we have indeed this received signal, the pilot signal as a tensor of dimensions MR at the receiver, number of antennas at the receiver, number of antennas at the transmitter, and number of training blocks. And it can be shown, this is provided in the more details in this paper, that this pilot signal tensor admits this decomposition in terms of the RIS receiver channel G, where is a partitioned matrix. Every block is associated with one group of the BD-RIS. Then we have the same for the transmitted to RIS channel, and then the scattering tensor that we call now scattering tensor, it's a tensor of dimension n bar q here times n bar q times k. Remember that the k corresponding to the number of states of your scattering tensor since you are training, right? So you are collecting measurements and you are changing the scattering, the impedances for every block to collect, and this is collected and represented as a third dimension of your scattering tensor. And of course, this is also appears here as a third dimension of the pilot signal tensor, right? So this is what we had before in the first slides, right? And then this is what we indeed exploit, which is indeed a rewriting of this equation. When you stack for all the blocks K, you stack them as the third dimension of this tensor, then we come up with this representation. And this is a block Tucker decomposition composed of Q blocks. If we, of course, this representation can be represented in a compact form in terms of if we just eliminate the summation over Q, then you get a block Tucker decomposition, or a Tucker equivalent decomposition in terms of the scattering tensor and the constituent channels G and H. Okay, so here from single to fully connected, at the end, I mean, these slides give you a big picture of what we had before with single connected RIS, which is indeed the one with n bar equal to 1 and q equal to n. So this is the traditional diagonal RIS, where this is the measurement matrix. The composite channel indeed has a Catirol structure. And then we have a scattering matrix, which indeed we use for also estimating these channels. And the resulting model is a parafact decomposition. If we go to the other extreme, on the right-hand side, if we go to the fully connected case, then we have this received signal model. The composite channel now has a Kronecker structure. And then the scattering tensor is, I mean, the scattering matrix here becomes a scattering tensor, n by n by k. And then if you have in between, you know, single connected and fully connected, if you have a group connected architecture, indeed what you have is a block Kronecker representation for your composite channel. And the scattering tensor now is a block sparse tensor where the scattering tensors of each group is indeed organized as in a diagonal form. When it comes to, because remember that our goal here is to decouple the estimates of G and H instead of estimating the whole T, the whole black box minor channel. We want to decouple the equivalent channels. And then one question that arises is, okay, but what is that procedure unique? Can you uniquely recover these constituent channels G and H from the tensor, the pilot signal tensor? So here we have the relationships for the different architectures. So if we go, I mean, this is for the fully connected case, which is the strongest connection degree that is possible, right? We can show that the estimated G and the H using this tensor approach, they are linked to the original matrices by a scalar factor, where these scalar factors, they compensate each other, right? So if you go to the group connected case, then this scalar ambiguity is confined within each block. So for every block, the corresponding matrix G and H, they are linked to each other and then up to a scalar factor that compensate each other. And then when it comes to the diagonal risk case, the ambiguities, they are indeed related by diagonal matrices that compensate each other. So what we can say about that is that when we have, I mean, the stronger is the connection degree of the BD-RIS, the less restrictive is the scaling ambiguity. And the less restrictive case is the least one, is where you have a fully connected RIS. And then we have different degrees of ambiguities depending on the connection degree and how strong is the connection between the elements. Okay, so let's come now to the algorithm, or how do we proceed to exploit this measurement tensor Y, the pilots, and then estimate those channels. So as I said before, we can unfold the received pilot tensor Y into three different forms. And we can show that in the absence of noise, of course, just to make things simple here, the three different unfoldings that we get by unfolding the pilot signal tensor, they respect these equations. So we have the two first unfoldings, they have the G and H on the left-hand side. Here you have the corresponding unfoldings of the scattering tensors. And then we have on the right-hand side, this Kronecker product involving the channels H and G. So, and then if you go to the third way of unfolding this tensor, you indeed arrive at a compact representation where you have here S of 3, and S of 3 is indeed, we call the compact three-mode unfolding, which is basically the concatenation of the three-mode unfoldings of for every group. And then you have on the right-hand side this Bloch-Kronecker factor involving the H and G. So as we are going to see, the first solution, which is the closed form one, it exploits the third mode unfolding by method filtering with the S3, since we are assuming that this receiver assumes that the scattering tensor is known. And then you do method filtering by right filtering the Y, the three-mode unfolding, and then you are left with this Bloch-Kronecker product, right? That you use for estimating the G and H. So the first step is right filtering. Take the measurement tensor, multiply by the conjugate of this compact three-mode unfolding of the tensor, and then this is approximately equal to this Bloch-Kronecker product between the two channels. And then, of course, since this is a concatenation of groups, we are left with Q problems to solve. So for every group, we will solve one problem to find the corresponding channels of that group, right? The thing is now, since we are left with this problem to solve, we can formulate as follows. For a given block Q, we want to minimize this loss function, the least squares fit between the corresponding Z of Q and the model, the Kronecker model involving H of Q and G of Q. This is a very classical problem, which is called nearest Kronecker approximation, or Kronecker factorization, or even least squares Kronecker approximation, and show that by just properly reshaping this matrix Z, we can translate this problem as a simple rank 1 matrix approximation problem, where the goal is to estimate G and H, and those are basically the vectorized forms of the corresponding channels H and G, right? So indeed, the idea here is for every block to solve this nearest Kronecker factorization problem, and then this can be used, I mean, you can solve this rank 1 approximation, let's say, using an SVD or any other, I mean, power method or any off-the-shelf rank 1 approximation scheme or algorithm available in the literature. So to recap, the solution is basically you start with the Z of Q, you apply, let's say, if you use the SVD as a representation. From that, you take the leading, dominant, left and right singular vectors, and that, of course, provide you an estimate of the corresponding channels up to that scaling factor I mentioned. And then once you do that for all the groups, you basically concatenate and you get the final estimates of those channels. The flow of the processing then starts with a least squares estimation by method filtering with the non-BD-RIS scattering coefficients, and then you have a kind of tree where every branch is solved independently for every group using this SVD-based solution. Here I show you some simulation results for the BTKF. Then you have what I show here just to make things quicker for the sake of time. So here we have the comparison between the least squares. So the traditional least squares method is shown here in this dashed curves, okay? And the BTKF algorithm they are all together here in this solid curve. So what we can see is that for a fixed overhead, if you fix the overhead K as the minimum one for the least squares method, right, which is 256, then the least squares receiver, the single connected case indeed performs better. So as you increase the connection degree of the BD-RIS, there is a degradation in the performance of the least squares method. In contrast, for the BTKF receiver, since you are exploiting the Kronecker structure of the composite channel, all the configurations, they perform quite close, independently of the connection degree. So that's the first message. And then on the right-hand side, if you now take a different criterion for comparison, so let's take the minimum overhead for every configuration. So as I mentioned, the overhead for the least squares is equal to n bar squared times q. So this is the minimum number of blocks. If you fix for every configuration the training size to be the minimum one, and then we compare, so we see that the least squares receiver, they have the same performance for all RIS configurations. So they are all together here in these dashed curves, superposed. And then in contrast, the BTKF, I mean, you have an improvement of performance in terms of NMSC as you let's say increase the group size. And the reason for that is that when you increase the group size, you have a more noise rejection gain that comes from the exploitation of this Kronecker structure. So, and the Kronecker structure becomes stronger as the connections between the BD-RIS elements become stronger. So there is a one-to-one correspondence between the connection degree of the BD-RIS and the noise rejection that you get by exploiting the Kronecker factorization of the composite channel. And then I will quickly present the second solution, which is the Bloch-Tucker alternating least squares method, which in that case, we do not use the third mode unfolding, which was the one we exploited for the BTKF, but now instead we exploit the other two unfoldings of the received pilot tensor. And then how we do that? Basically, by using these two unfoldings, we formulate these two least squares cost functions. And if you see here, each cost function is related to the estimation of one matrix. So the first one is associated with the estimation of G. And then the second one, we assume that G is known, and then you optimize with respect to H, and then you find the best H. Since these two cost functions, they are intertwined because one matrix depends on the other one, right? One optimization depends on the other one. The classical way to solve this problem is using an iterative alternating least squares estimation method where, let's say, you initialize one factor matrix. In this case, we initialize H, let's say, and then you find the best least squares solution for G. You plug the solution for G here in the second cost function, and then you find the best H. So indeed, what the BT-RIS does is that you optimize these two cost functions in an alternating way until convergence. This one of the main advantages of this BT-RIS method is that the training overhead is significantly reduced compared to the other state-of-the-art method. So we can show that the minimum K that is necessary to identify, to find the unique matrices G and H from those problems is related by this expression. So if you see, this is quite less restrictive than the previous ones. We can, for instance, work with a training size that is much smaller than the product n bar squared times q, right? And this is one of the main features of the BT-RIS algorithm that comes from exploiting the tensor decomposition structure of the pilots, right? Here I just show in terms of convergence to convince you that indeed this iterative procedure, it converges, usually converges monotonically. And here I show the reconstruction error in the noiseless case, right? Just to validate this algorithm. And then we test different configurations and then what I would like to point out here is that this is for using as few as 40 blocks. And then here you have a system with 64 elements, and then you use, of course, the K is much smaller than n bar square times Q, right? And still the method works, and it converges within 40 to 50 iterations for those setups. And on the right-hand side, I show when now we add noise, and then you change the noise power, then you vary the SNR. Then this is the number of iterations that you need to converge, depending on different SNRs for an actual training using this convergence criteria, right? Based on the difference between the errors, the reconstruction errors at every iteration. And then we stop when the algorithm reaches 10 to minus 6. And using this criteria, you can show here more or less that the convergence, of course, the algorithm needs less iterations as, of course, less noise you have. And that converges to around 20 iterations in the high SNR regime. And in terms of performance, I will focus on this figure here. What we can show on the left is that here we test different configurations, different connection degrees and group sizes, and then for 32 training blocks. And we can see that the algorithm becomes a little bit kind of insensitive to the connection degree. So as long as the overhead is satisfies that condition I showed before, so the algorithm behaves more or less similarly for different architectures. And then of course, there is a price to pay, no free lunch here, as usual. So on the right-hand side, what I show is that if we compare now least squares, which is the black curve, BTKF, the first tensor method is in the blue curve, and then the BT-RIS for two different SNRs. What we show, of course, is that the computational complexity of the BT-RIS is higher than that of the squares and the BTKF, which are the two closed form methods. So this is kind of, is the price to pay in terms of complexity for affording a very low training overhead. I will skip the design of the BD-RIS because, I mean, just one quick comment is that these results, they suppose a proper design of this BD-RIS training tensor, scattering tensor. And this is not a very trivial task. We spend a lot of time trying to find the best way of designing those tensors in order to ensure the uniqueness of the two channel matrices. So I will not provide the details here. You can check in the paper. Of course, I will also be happy to answer, to clarify if you have any comment about that. But indeed, there is a design that ensures a good, let's say, property for estimating those two channel matrices. Okay, so that leads me to the summary of the talk. So basically what we try to show here today is that there is a link, a fundamental link between tensor decomposition and the BD-RIS channel estimation problem. Exploiting this link, we can achieve channel decoupling, so estimating the two channels separately with a good accuracy. And there are two solutions so far to solve this problem. The first one, BTKF, is a closed form method that has low complexity, enjoys parallel processing for every group. This is very important for low latency communications, right? Where you want to decode and to estimate those channels fastly. So that's one of the main features of the BTKF. On the other hand, we have, let's say, the workhorse method because it's an iterative solution. It has a very low training overhead compared to the first one. But of course, with a higher complexity, is an iterative method that requires matrix inverses. Although those inverses can be simplified by exploiting, block sparsity of the problem, etc. I didn't address this point here. But then there is, of course, a trade-off between the two methods, right? And as usual, we have some perspectives here related to this recent study. So we believe that there's maybe room for exploiting new training designs for the scattering tensor. We have proposed one way of doing that, but there might be other ways or smarter ways of doing it to improve the performance or even to reduce the overhead. I also believe there is a further study to be carried out on the uniqueness of this tensor decomposition. Maybe we can come up with more relaxed or even more general uniqueness conditions. And we don't have so far we don't have a rigorous proof of the minimum overhead for this solution. This is still an open problem. Another thing that I find interesting is to consider other RIS architectures, such as, tree connected, forest connected. So linking this problem to the graph theory. And then, of course, there might be a relationship between the connection topology and then the way how you design your scattering tensor and the way you proceed. And finally, of course, exploiting, especially for higher frequency bands, if we exploit the sparsity of the problem that has not been exploited here, if you use kind of, this multipath, low rank representation for the channel matrices, we can, of course, achieve a further reduction on the pilot resources. So there is still room for improving the training overhead, I believe. Okay, all right. So thank you very much. I mean, I'm sorry for taking 10 minutes more than I expected. I hope that it's not a big problem. And then, I'm very happy to take questions. Thank you.
Thank you so much, Andre. Very interesting.